Conformations of cyclohexane. Have you got it? This short video quiz assesses your understanding of terms relating to conformations of cyclohexane, including chair, boat, axial, equatorial, cis, trans, and 1,3-diaxial interaction. Your ability to understand and draw depictions of stereochemistry in relation to cyclohexane rings, and your ability to compare two chair conformations of a substituted cyclohexane in terms of conformational energy. The quiz consists of 3 questions. It's meant to be taken after you've studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself, and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1. In each case, identify the indicated groups as axial or equatorial, and how the specified pairs are cis or trans. Find all 1,3-diaxial interactions. Okay, so pause the video while you answer this question. Do it on paper. Think about it. When you're ready, come back, and we'll see how you did. Okay, we're back. Axial or equatorial? Let's start with the equatorial. These are relatively easy to find because they are on lines that are parallel to ring bond. 1, 2, here's a ring bond, here's 1, here's 1. There we go. Axial are the other ones. They will point opposite each other on the ring if there's more than one, generally, or parallel, but not parallel to any bond that's on the ring. These 5. Okay? Now, cis or trans, A and B. One is pointing up, one is pointing down. These 2 are trans. B and C. One is pointing down, the other is pointing down. These 2 are cis. Cis or trans, C or D. One is down, one is up. See how the bond is a little bit up? So those 2 are trans. Over here, well, you know, this might be really hard to see it unless we rotate the structure just a little bit, but we're saying, are they pointing to the same side or the opposite side of the ring? So F and I, okay, very definitely pointing opposite each other, definitely trans. H and I, very definitely pointing in the same direction, they're cis. F and G, okay, pointing down. F and G are cis. Cis, 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 cis. Here's another cis, by the way. Okay. Find all 1,3-diaxial interactions. Well, these are axial interactions that are in the same direction on the same side of the ring. So that's H and I. And there are no other 1,3-diaxial interactions. How'd you do on that? Number 2, in each case, indicate the conformation that is lower in energy, or if both are the same energy. Pause the video. Think about this. Write a few notes. Come on back and let's see how you did. Okay, we're back. We're going to look for axial groups first. So in this case, in the case of 1, here we have a really strong 1,3-diaxial interaction. It's a really bad one because it's a methyl-methyl interaction. So the lower energy is going to be this one that does not have that 1,3-diaxial interaction. Okay, what about this next one? There's no 1,3-diaxial interaction. There's an axial group in each case. There's an equatorial group in each case. Pretty much, what else can we say? There's one gauche interaction between those methyl groups, so that's the same. And in fact, these two are the same energy. Okay, how about this last one? Well, in this case, what we see is a boat conformation. And the chair is always going to be better than the boat. So the more stable conformation is the one on the right, the chair. All right, ready for a challenge? Draw the two chair conformations that would be in equilibrium for each of the following compounds. Indicate which is lower in energy. Now, this is going to take you some time. This is not a trivial thing to do. I recommend starting out by drawing a cyclohexane, something like this. In each case, getting the various groups around that the appropriate way, whatever way works. Your next job is to draw the corresponding ring-flipped version, where perhaps this carbon that we see right here is now this carbon right here. All right, good luck. See how you do. This is actually a very tricky problem. In fact, what I'm going to do is give you a little hint. I mean, just a way of starting this so that maybe we all are doing it kind of the same way. What I'd like you to do is take this carbon right here where I'm drawing the spot and make it the carbon that I've indicated with the spot in each case, okay? And then do the same thing with this one and this one. And let's see if we get the same structures. Okay, pause the video. We'll see how you did in a few minutes. All right, we're back. I'm going to start by drawing these templates. Okay, and my atoms are right here. And I'm talking about with the spot. All right, in the first case, I have a methyl that's up and an isopropyl group that's up. So we're going to go up and up. And next one, I have over here a methyl group. That's going to be the one on the back for me. That's up. Then I skip and I go another one up. And I skip and I have one that's down, which is the equatorial position. All right, and the last one. This one is up. This one is up. And this one is up. For my other structures, this one is up. And on the other side, it's up. Okay, the next one. First one is up. That would be this. Next one is up. That would be this. And the last one is down. That would be this. Finally, 3 up. So up here, up here, up here. So this is equatorial, axial, axial, equatorial, axial, axial, equatorial, 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 axial, axial, equatorial, axial, equatorial, axial, equatorial. In the first case, we have an axial group and an equatorial group, but we want the biggest group to be equatorial, so here's our favorite energy. Next one, 2 axials and an equatorial versus 2 equatorials and an axial. We're going to go for the 2 equatorials and an axial. And finally, the last one has 2 axials and equatorial, and the other one has 2 equatorials and axial. Once again, this is the structure. Now, I know the really hard part here is just getting the directions in the right way. So one of the things you might want to practice is drawing this cyclohexane and then getting all the equatorial bonds in the right place and all the axial bonds in the right place. Like that. And for the other ring system, see these two bonds here? So I'm going to draw these two over here equatorial. I see these two bonds here. Oops. These two bonds here and here. And I'm going to go in between them and draw the two equatorial bonds. I see these two bonds here. And I go in between them and draw the equatorial in the same direction. And then the axials are sticking up on the top, every other carbon, and on the bottom, every other carbon. Now, that's pretty tricky. And I want to show you another way to do this that does not involve drawing two conformations with all these fancy chair, that still gets us the information about which one of the two conformations is lower in energy. Think about this. I'm going to draw one of the conformations of cyclohexane. I'm going to notice something in particular. Okay, here's the interesting thing. We're going to label these axial and equatorial. The equatorial ones are actually relatively equatorial, like around the equator, right? And the axial ones are axial, like around the axis of a spinning top. Now here's the deal. They alternate on the two faces of the ring. Now when I mean a face, I mean we're going to call this the top face and this the bottom face. The top face is the face that we're going to draw wedges to in this kind of drawing over here. And the bottom face is the one we're going to draw hash lines to in that sort of drawing. Have you got that? Now watch this. In the top face, if we go around the ring, look how it goes. Axial, equatorial, axial, equatorial, axial, equatorial. Around the ring, axial, equatorial, axial, equatorial, axial, equatorial. Okay, take this first one. We know that we want the biggest group in an equatorial position. That's got to be this isopropyl group. And that means if we go around the top face, every other one, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, that this other group over here is axial. There you go. That's it. All you have to do is draw one conformation like this. Make sure you pick any carbon, whichever that you want, that has the isopropyl group on. I'll choose this one. No, wait. It's got to be one that's pointing up. So it's not just any carbon. It's this one. Watch. See, now there's an equatorial that's up. And then I go around the ring. 1, 2, 3. And this axial, this one, this other one on the same face is axial. And there's your lowest energy conformation. Okay, let's try the second one. Okay, we know that we want the most groups we can get equatorial. So let's just pick one of them and call it equatorial, like that. What are the other two? Well, along the top face, it goes equatorial, axial, equatorial. All right, and we keep going. On the top face, equatorial, axial, equatorial, but that's not on the top face, that's on the bottom face, so it must be axial. So here's a version in which we have two equatorials and an axial. If we started the other way, and we happen to choose this one over here and said, I'm going to make this one equatorial, then we'd go equatorial, axial, equatorial on the same side, but this is the opposite side, so that's axial, and now equatorial, axial on the same side. So here, this one with this methyl group equatorial, there's two axial, and what we had before was equatorial, equatorial, axial, with two equatorial and one axial. So this is going to be the most stable. All right. Again, you just draw the cyclohexane however you like to draw it. Make sure that you find an up position that's equatorial. I'll pick this one right here. Up, equatorial. Move around the ring. Up, equatorial. Two more, and then down, axial. Right there. And that's it. How about this one? 3 in a row. We want the most equatorial. Well, we know it's going to go either equatorial, axial, or axial, equatorial, axial. Well, we want to go equatorial, axial, equatorial. So we have 2 equatorials plus 1 axial. Here we go. Pick a carbon where there's an equatorial up. I'll go way over here. There's that one. We'll do that one right there. And then the next one is axial. And the next one is equatorial. And there you have it, the lowest energy conformation in each case. Something to think about. There are multiple ways of doing these problems. Okay, now here's a really good trick. Let's say we need to draw the 2 conformation, the other chair. In this first case, we draw the same chair. In fact, you already may have noticed that this is the only one I can really draw well. I want to draw the equilibrium other chair conformation. I can actually draw exactly the same ring. All I have to do is rotate the positions one place. So for example, see this isopropyl group here that's equatorial. Well, that carbon is this carbon over here, right? I shift over one position to the right and I draw that. It has to be axial because it's up. And I go 1, 2, 3, 4 carbons. 1, 2, 3, 4, and I draw an up. Well, look, it's equatorial. And that is exactly the opposite of what we have in the first case. This one over here is simply a different view than you're used to seeing of the equilibrium conformation, the other conformation. Here we go. We'll do it down here again. Okay, let's say we want to show what it's in equilibrium with. I do not have to learn how to draw the other chair. All I have to do is draw the same chair I like to draw, but I rotate the positions one. So this methyl becomes this methyl. This methyl, 2 away, becomes this one. It's down, and it has to be equatorial. 2 more away. It's here, it's up, it has to be axial. Now, this one over here, I'm going to draw the equilibrium. I'm going to draw the same chair. Look at that. But now I'm going to rotate everything one position to the right. Instead of being over here, we're going to be over here. Instead of being over here, we're going to be over here. Instead of being over here, we're going to be over here. This first one, up, axial now. This second one, up is axial. Well, now it's flipped. It's equatorial. And the final one is equatorial. Well, now it's flipped. It's axial. The key is that in each case, whatever is up here has to be up here. Whatever is up here has to be up here. In the second case, the one that was up here is up here. The next one's up. The next one's up. The next one's down. The next one's down. Just like that. The equatorial, in the first case, the isopropyl group is up. It's up. It's up. The methyl group is up in the picture. It's up in this picture. And it's up in this picture. It's the up and the down that we keep exactly the same in all depictions of cyclohexane, no matter how we do it. That is a key to making this work. When you flip a ring, every axial becomes an equatorial, and every equatorial becomes an axial. All right. Remember, the boat conformation of cyclohexane is very high in energy due to severe eclipsing within the ring. This means that you will never see a boat conformation that is lower in energy than a chair conformation. Chair conformation will always beat out the boat conformation for energy. And when drawing chair conformations in cyclohexane, all the groups pointing up are cis to each other, and any group pointing up is trans to any group pointing down. Well, I think that's it. I hope that helped, and I hope you've got it. But if you don't, practice. Well, the last thing I would say here is that drawing these cyclohexanes really, the last thing I would like to say here is that drawing cyclohexanes is a skill. It takes practice. You've got to practice. Do the best you can to communicate what you're trying to communicate. And don't worry about being a superb artist in doing it. Just make sure you're communicating. Make sure those equatorial bonds are pointing in the correct direction. Make sure the axial bonds are pointing in the correct direction. All right, so I hope that's helped, and I hope you've got it.